Welcome to High Tech Heroes, the program that takes you behind the scenes of today's high-tech industries, where you can meet the people and examine the ideas creating tomorrow's technology. And now, coming to you from the studios at Foothill College, high atop the mountains overlooking Silicon Valley, here's your host, Sherwin Gooch.
Bonsoir, I'm Sherwin Gooch. Welcome to High Tech Heroes. Our episode this week is a continuation from last week. As you may recall, Seymour Cray was relating his difficulty in making switching devices from a new material, gallium arsenide, because of the widely varying performance characteristics of the gallium arsenide available. He was comparing his current difficulties with the difficulties he experienced 30 years earlier while he was using the new switching material, germanium, to design the first all-solid-state digital computer, the 1604. The surprise is that he is presently using diode transistor logic. DTL is not currently in style, but it's the same circuit which Mr. Cray used all those years ago to correct for the widely varying performance characteristics of early transistors. And now, let's join one of my heroes, Mr. Seymour Cray, whose speech is already in progress.
And here comes gallium arsenide for real. And so I want to give you my impressions of the potentials and the problems and where we are in terms of using gallium arsenide for logic. There's no way right now we can use it for memory. So the Cray 3 computer is a combination of gallium arsenide for the logic and silicon for the memory. Not as incompatible as you might think, because the way that we're using gallium arsenide, very primitive form. It's called diode transistor logic. It's the same as the 1604 was 20 or so years ago. The reasons are the same. Gallium arsenide circuits are quite unpredictable, very non-uniform, and so the arguments for very early silicon circuits are the same arguments today in the choice of configuration. What excites me about it is I know what happened during the 60s after this primitive form, and I certainly hope the same thing happens in gallium arsenide during the 80s and 90s, because it seems like the potential is there. So what I'm trying to say is I think we're on the front end of something using gallium arsenide for logic, because we're accomplishing a factor of 3 speed improvements serially using very primitive circuits compared to the silicon versions we're comparing against. Now, when you talk to research people about gallium arsenide and you ask them why are they faster than silicon, they talk about electron mobility. 3 times electron mobility, or perhaps they use a little bigger number. And I never quite understood electron mobility. I was thinking about something else, which is capacity. And the interesting thing to me was that gallium arsenide is an insulator. Silicon is a conductor. And so when you look at the integrated circuit design, you find you can work with much smaller capacitances on gallium arsenide because of its insulating property than you can on silicon, because you've got a conductor right next to it. And so I began a development program, which again is really interesting. In beginning the Cray 3 work, and it was just about 5 years ago, I went back to Rockwell, and again the interest was rather minimal, but there's a group of people there who were leaving, spinning off a new company called Gigabit Logic. When I talked to silicon people about integrated circuits, when I talked to Rockwell about gallium arsenide circuits, they all gave me a big book of rules. And one thing about people that develop circuits without knowing about computers is they make rules that makes it very hard to make computers. So when I talked to the people at Gigabit, they said, geez, we don't have any rules, we're just starting our company. So I guess you'll have to help us make some. And I smiled. Here was a blank piece of paper, and I really love blank paper. So we got started off working together, and I finally learned the basics of field effect transistors, insulating substrate, Schottky barrier diodes, which come for free in that business because all you need is a little metal on the surface and you got a diode. And so in a period of about 9 months, we put together very workable gallium arsenide circuits using exactly the same circuit that was used 20 years earlier in silicon for the 1604. So we're pretty well launched. And we've been working together now for a number of years. And we're in production at last. The interesting thing is, as I started looking for a second source for gallium arsenide, went around to all the bigger companies, and they all told me the same story. They said, we have such a big investment in silicon facilities, gallium arsenide just doesn't fit in. We really don't want to fool with it. So I thought, thank heaven for startup companies, or we never make any progress. And it's interesting, in our country, there are so many spin-offs with new ideas. I think it must be the greatest strength we have in a technology sense, because people who get unhappy with structure in companies can move on, start their own, take the big risks, and occasionally find a pot of gold. And I think that's just wonderful. So let me talk a little more now about the Cray 3 computer specifically, how it's implemented, what the promises seem to be, and what the problems are. I've got a few slides I'll show in a minute, not very many, but give you a little background. First of all, what is the potential here? Well, the claim is that the Cray 3 computer will be 12 times the computing power of the Cray 2. Now, I said it that way very carefully because those of you who don't believe in parallel computation in multiprocessor machines would have some question about that number. So I'll separate it for you. Seem to have a factor of 3 speed linearly for every processor, and we can have 4 times as many processors for the same dollar investment. So there's the factor of 12, and you can use it in your own mind however you like, but it seems to be quite significant in any case, because 12 is an awfully big number. So that seems to be the opportunity. Now, what are the problems? Well, gallium arsenide is pretty horrible to work with in a process sense. It has a lot of grain. It has different grain in all 3 dimensions, because it seems to have a 3-dimensional structure, that is a rectangular structure. Electrons flow one way in one direction, different in another direction, and different in a third direction. So you have to line up all your circuits to use the grain of the crystal. Well, that's kind of tough. You've got to be careful to get everything lined up right. But then it's worse than that, because it's sort of like getting potatoes. There's hard spots and soft spots and knots and eyes, and it's very hard right now to get basic material which doesn't have flaws in it. But getting better every year, and Gigabit seems to be getting pretty good stuff, and right now we're getting a 50% yield on our integrated circuits for the Cray 3. And that's good enough to make machines, and we hope that goes up to 60 or 70% before long. And then we will have accomplished our financial objectives of being very competitive. So that's pretty much the story in terms of the speed of the circuitry.
Starting around 1955, Seymour Cray had begun to surprise the world every 5 years or so by building the biggest, fastest, and most powerful model of computer available. Every time we were amazed because the size and speed of each new computer he built was always beyond our expectations. Around 1970, he did it again by announcing the 7600, a machine with a central memory so large as to be unimaginable, and a speed derived from the time it took signals to travel between components at the velocity of light. We were amazed. We didn't see how any computer could ever be built which would surpass the 7600. And what did Seymour have to say about his new machine? I'll never again build a small, slow computer like the 7600.
life ahead. I wanted you to know how I feel about you. That's why I said, be smart, don't start. Be smart, don't start. Drinking hurts.
Want a drink? No thanks.
Don't start. Be smart. Don't start.
And now we return you to our afternoon movie, What's All This About Gallium Arsenide, starring Seymour Cray, with guest appearances by Jack Worlton, Jeffrey Deutsch, Chris Norrie, and Steve Wallach.
So that's pretty much the story in terms of the speed of the circuitry. In terms of other characteristics of the Cray 3, we're taking a little clue here from our brethren. You know, in Cray research we have competing groups. We have our letter group of designers and our number group of designers. We have the XYZ group and we have the 1, 2, 3 group. I work with the 1, 2, 3 group. But the XYZ group has been doing pretty good lately. And they had more parallel structure in their machine than we did in the Cray 2. Dual access to common memory and different kinds of access structures that help. And so those are being incorporated into the Cray 3 as well. So we expect to see quite a significant increase in performance. And we hope that this will all happen next year. This is the year of the YMP first delivery. Hope next year will be the first year of the Cray 3 delivery. How we've been so lucky to have these two groups, and they seem to go through history one foot in front of the other and stagger out. This was not planning. This was sheer luck. And it seems to be working pretty well so far, so we won't change our direction. Anyway, couldn't find a slide of the original Cray 1, but Cray 1S is pretty close. The reason to show it here is look and think for a moment about the numbers, because when I come to the last slide, I'm going to put them all together in a chart for you. But here is a single processor machine. Clock period is 12.5 nanoseconds. 80 MIPS is the hardware speed, and 160 megaflops. Here's the packaging. This module I think many of you have seen. You know, it takes two hands to hold it. It's pretty heavy. It's really two-dimensional in the sense that there is a very minimum of interconnection between the two boards and the two sides of the module. And I want to contrast that with the later modules, which are truly three-dimensional. The circuits here are packaged in a very conventional way, hermetically sealed, have leads you bend and poke through the board. 4 gates, silicon. Here we see the Cray 2. Now, this is the one I struggled with because I couldn't get fast enough parts to do what I wanted, had to make do. Memory is really PC computer memory. As many of you know that have run programs that are memory limited. That's too bad, but you had to use what you could get. Likewise, the silicon circuitry. Not really much faster than Cray 1, but larger scale integration. So there was some progress, and in a vector sense, we achieved essentially the goal I wanted, which was 4 nanoseconds. Came close enough, and managed to get 4 processors in the machine at essentially the same cost as the Cray 1. And we allow for inflation in the period in between, keeping a fairly constant cost from machine to machine. Number of MIPS is up substantially because of the 4 processors and because of the clock rate. Likewise, megaflops. The really exciting thing here was to use liquid immersion cooling. When I first talked about liquid immersion cooling, everybody in the project laughed. In fact, they rolled in the aisles. Because everybody knew the boards would swell up and it just wouldn't work. Nevertheless, we needed something pretty dramatic because we weren't getting very far with cooling with metal conduction. With the densities one has to have, the speed goes up. So we tried it, and what do you know? The boards didn't swell up. Actually, it worked pretty good. And today, I believe that Cray 2 reliability is as good or better than most anything else you can find. And a lot of the reason for that is the liquid immersion cooling. There's very little temperature difference between the parts during warm-up and during normal operation. And so we have good temperature stability, and that's a real key to reliability in the long run. Now, notice the person standing here, because that person is going to appear next in the Cray 3 slides. Not the immediate one, but the following one. Same person, all right? This is the Cray 2 module. Now, I thought this was truly three-dimensional. It isn't a cube, not physically, but it's a cube electrically. Because if one counts the number of lines that are going in the X direction and the Y direction on the boards, the foil runs inside the printed circuit boards. You count those numbers, and then you count the jumpers that are going perpendicular to the board. You find that the populations in all three directions are nearly equal. And the preferred one, of course, is the one that goes vertically because it's so short. And so the machine was organized for the really critical transmission paths to be vertically through the module. There are 8 boards here. And so if you looked at it electrically and you counted the integrated circuit packages, it's 8 by 12 by 8, which is very close to a cube. So I was pleased with this, and with the liquid cooling, it seemed to work just great. And although the circuits were slow, we did the packaging job. That's how I felt about it. You notice that the logic levels per clock period is only 4, and tradition is 8. And that's where you find the scalar performance slipping with respect to vector. No point in slowing the vector down. Might as well do whatever you can. But this caused an imbalance between the scalar and vector performance, and it was strictly a function of the slow circuits. Here we see the same person in the Cray 3 computer. Now, here the clock period has dropped to 2 nanoseconds, but the level of logic is 8 again. So here is the dramatic increase in serial speed. It is essentially 3 times what we can do in silicon today with equal effort, equal teams. We're comparing 2 nanoseconds with 6 nanoseconds with the same amount of logic being done per clock period. We have 16 processors, so there's the other big factor of 4. And now the numbers are getting more zeros after them. We have 8,000 MIPS and 16,000 megaflops. And we have gallium arsenide, which is the key to the serial speed. Now the module is getting pretty tiny. It weighs 8 ounces, and it's practically solid metal. And I hope you can see that there is a 4x4 array of 1-inch circuit boards. These are stacked vertically. And this is very high density packaging compared to anything else we've attempted. And the reason is it has to be to go with the gallium arsenide. If you have a factor of 3 improvement in circuit speed, you have to reduce the linear dimensions by a factor of 3. That means reducing the volume by a factor of 27. And that's not easy. If you figure the volume of the electronic part of a Cray 3, 16 processors, 512 million words of memory, the whole thing is less than a cubic foot. The rest of that is all power supply and cooling support. But the challenge here is twofold. One challenge, of course, is to package the gallium arsenide circuits in a way that will fit in the structure. Well, most people who we talked to about packaging just cringed at the requirement here because there's no room for a package. We have to package bare die. This whole package is only 1/4 of an inch thick, and it has 4 layers of boards, 4 sets of die. And in order to do that, not only do we have to package the die without, mount the die without a package, but we have to grind the die down thinner than they come from the foundry because there just isn't room for all that die material. That's the part most everybody couldn't believe. Wafers are usually processed around 25 mils thick, and we have to grind them down to 12 mils because we save half the space in the computer that way. And that seems pretty weird. But if we didn't do that, we'd have a module that was almost 1/2 an inch thick, and the whole thing would be slower by a significant factor. So we do terrible things to these little gallium arsenide die. We grind them down, then we bond great big gold posts onto them. Not little wires, but big gold posts, 3 mil diameter posts. The reason for that is the mechanical bonding of the die to the board is done with the same thing that makes the electrical connection. Namely, these gold posts go right through these little tiny boards and get crimped like a rivet, very soft gold rivets. And we bond then 16 die to each of those 1-inch boards. We have a total population of 1,024 fairly large-scale integrated circuits in this area of 4 by 4 by 1/4 of an inch. There are 4 of these modules in a Cray 3 processor, 4 by 4 by 1 inch. And that's a real advantage in the sense that the wires mostly disappear. And we have wires between them, but no big number. And so the path lengths have dropped by, indeed, a factor of 3 linearly. Typically, the average path is right around 1 inch. And that's dramatically reduced from anything that's been done before. The liquid flows right through these modules, not perpendicular, but longitudinally. Total path for the liquid is the 4 inches you see, because these modules, 200 of which make a 16 processor machine, are arranged in a circle around the top of the tank you saw. The liquid flows vertically right up through the module, flows around the die, and goes back down a supporting pipe between the octants in the machine. So total fluid travel is 4 inches, and velocity is 10 inches per second. Those numbers come out to be a very modest temperature increase over the surface, and it's quite comparable to the Cray 2 in terms of total delta T. So here we have 200 to 400 gates. 500 is the maximum that we can have in a package. Gallium arsenide circuits. 4 modules make a processor. 200 make a whole machine, including the memory. And the logic levels, if we take into account all of the paths, average out to be 6, which is about the same as it has been with 8-level logic machines. Here is the overview of system performance in the machines that I've been working on. And what I want to point out here is the vertical scale is logarithmic. Horizontal scale is linear years. Well, those of you that plot things on log paper know it's very hard to make curves go upwards on log paper. So I'm very proud of the fact that there's an upward inflection where gallium arsenide comes on the scene between the Cray 2 and the Cray 3. This is a big increase. Cray 4 is a continuation of the Cray 3. We'll talk about that a little more in a minute. But it's evolutionary, and you see we go from 16,000 M-flops to 128,000 M-flops in a period of 4 years. So we think we're at the beginning of something with this technology, and there's quite a long ways to go, and we're going to go just as fast as we can. And that's MIPS, and again, see the big inflection. There's even a larger inflection here because in the Cray 2 we could only issue instructions every other clock period. Not enough levels of logic. Here we have enough levels of logic so we can issue every clock period, and so it makes that curve even steeper. Tell you just a little more about what's happening right now, and then if you have some questions, I'll be happy to make up answers for them.
We were talking about the 7600 earlier, and I thought you might want to see a part of a 7600. Bob Zaleski was kind enough to loan us this example of 7600 technology. If you look closely, you can see the individual transistors in the tiny cans over here on the PC board. Even though integrated circuits had come out before Seymour built the 7600, he used discrete transistors because they could be cooled more efficiently. This allowed them to be driven harder and therefore faster. A number of PC boards like this are assembled to make a module like this over here on the right. Modules were assembled into 4 walls resembling a cubicle, which was a 7600 computer. Be sure to watch High Tech Heroes next week at the same time when Seymour Cray will answer questions posed by many famous industry experts. Au revoir.
Thank you for joining us this week for High Tech Heroes. Be sure to tune in again next week when we will bring you more entertaining information about the people and ideas behind the scenes in today's high-tech industry. And now, this is your announcer, Bill Weigel, wishing you the best of luck and a pleasant week. Au revoir.
Videotaped lectures of many industry leaders are available from University Video Communications of Stanford, California. This episode of High Tech Heroes has been made possible in part by grants from Supersoft Incorporated of Sunnyvale, California, Kinetic Microscience, San Jose, California, Cybernetic Arts, Sunnyvale, California, Big D Closeouts, Sunnyvale, California.